Number one, DQOs for environmental sampling. Well, I think probably everybody knows what they are, but just in case this is not part of your ballywick, and for Mark's edification or benefits, so you're up to speed, DQOs are qualitative and quantitative statements that are meant to do several things. The first, and perhaps the most important, is to clarify the study objectives. It sounds pretty basic, but when EPA started writing DQOs, that really wasn't a big deal. I remember back in the early days of, say, Superfund, where people really didn't know what the objective was. They didn't understand CERCLA, RCRA, anything like that. And so they were out there just taking data, okay, collecting samples, and they all thought that was good without any real objective. They just wanted to get data. Well, unfortunately, and especially under Superfund, which was so litigious, that they didn't realize they were also collecting evidence, okay? And it came back to bite a lot of people in the end. So defining the objective can be actually one of the most difficult, what I call global issues of the whole project. What problem are we trying to solve? The data should be used for decision making, and therefore, what is the objective of that decision? Once you figure out what you want to do with it, you figure out what are the most appropriate data. As we'll see, there are lots of ways to collect data, different types of samples, the timing, where to put them, and so on. What are the most appropriate data to collect? We have lots of choices. And sometimes it's determining the most appropriate conditions. This is especially true for fluids like air and groundwater. Also, along with the DQO process, in fact, one of the major steps is figuring out how much uncertainty or error in the decision that you're willing to tolerate. That's really the key for statistics, is to put that ceiling on the uncertainty and the decision error. Okay, and we can do that. We do that via the data we collect, so that's how it gets wrapped into the DQO part. But it's a very, very important process, and we'll go through many ways in which we can design a study to limit the amount of decision error in the project. They're used to determine the quantity and quality. These are kind of two different areas. The quantity is the statistical world. That's what I'll talk about more. Quality crosses both worlds. It crosses the sampling and statistics, but it's also going to focus on the laboratory. We won't talk too much about the laboratory side of the house today. That's not my background, and certainly someone else could do a better job with the environmental chemistry issues along with that. But they do come into play with things like park parameters and so on. And then finally, they're used to develop a scientific and resource-effective data collection system. This was even more important in the early days when EPA was funding a lot of Superfund projects, and they wanted to make sure that their own resources were used wisely, which was a good thing. And there are ways to optimize the number of samples you take so that you get the maximum amount of information for the minimum number of samples that you have to purchase, especially if you're using contract lab versus, say, field analysis. Now the alternative, and I alluded to this, is problematic. And this is kind of one of those silly takeaway slides that I want you to go home with. Sampling without DQOs. Sounds silly, but it's really the case. And it reminded me of Alice in Wonderland, where she meets up with the Cheshire Cat. And she tells the cat, or asks the cat, which way should I go? And the cat said, well, that depends where you're going. And Alice said, I don't know where I'm going. And I said, well, it doesn't matter. And that's the way some people would like to run their projects. But that doesn't help you, okay? You need focused data. You need the data that people are going to, or the data that will tell you what decisions you can make, whether it's okay or whether it's not. And so DQOs are a very important part of the upfront planning process. EPA recommends a systematic planning process, and DQOs is part of that. It's a plan in the planning process, do, and then check. Okay, sort of a circular cycle. And if you have to do it more than once, then so be it. Hopefully we don't. In general, what is the DQO process? They actually based it on the scientific method. There are elements of structured planning and structured thought that go into it. It's a 7-step process, so you have to go through each step. You have to go through each step in sequence. You can't skip from one to another. When you get down to the end, we'll see that you can kind of cycle through the last 2 steps a couple of times if you're not getting quite the data that you like. Again, strategic planning, but it answers some very, very important questions. When do we sample? Where do we sample? How many samples? And what are the tolerable limits of error? The 3 questions I get in any industry when I look at a sampling design that we're about to implement is basically, how many samples do we need? When or where do we take them? And how confident am I in the decisions I make based on the data we receive from our sampling effort? And I don't care what industry you're in, people always want to know those same 3 questions. And the lawyers always want to know those same 3 questions, although fortunately they've not been as active lately as they were, say, 20 or 30 years ago. The agency had a goal for the DQOs. They wanted to define the type, quantity, and quality that will be used to make appropriate decisions, and that resources would not be expended to collect data that weren't needed. So, as you can see, EPA is focusing data along with a decision. Okay, so basically the idea is anytime you're collecting data, there should be an associated decision. You shouldn't just be out there collecting data for fun or really for scientific research. That's something else other people can do, and that's fine in their world. But we're focused on cleanup or remediation and characterization for potential cleanup and so on. So we want to make a decision. So if you're just out there getting data because you're interested in what's going on, that's not a good program. Okay, you want to be focused on what you're going to do with the data. And it could be a simple answer, just like, is it there, presence or absence, as long as there is a decision to be made. Now, the nature of data is such that it poses a few constraints on us. It's dependent on the collection systems we have and the sampling devices we have. For instance, in groundwater, the collection system is a well. Well, that's a fairly complicated system. It takes a lot of time, money, skill to install it correctly, to monitor it, and then the sampling has its own special problems. Sampling devices in soil are many, and some are good, some are not so good. In fact, we'll call them correct or not correct as we talk about sampling theory tomorrow and how to take good soil samples with the pastas. Data errors are frequently introduced by the sampling, and that's really one of the main themes and another takeaway from this course. Data errors are frequently introduced during the sampling process, and a lot of times, in fact, probably the majority of the times, the lab gets the blame. Now, you may have been on a project where you sent in, say, some soil samples, and the first analysis for lead came back at, say, 5 parts per million. The next one came back a duplicate at 500. Okay? So everybody scrambles around, and where do they look? Start going through the lab records and the data quality and, all that kind of good stuff. A good portion of the time, it wasn't the lab's problem. It already happened a long time ago. Or maybe it did. It was in their subsampling process. But people weren't looking there. And so we'll talk about incremental sampling and G's sampling theory and how to mitigate and control those types of errors and how to try and make duplicates, for instance, as close in value as you possibly can, because no one likes to wonder if it's really 5 or really 500. Even if it's only 20%, you still want to know which one is it. It's, as they say, it's like the guy with 2 watches. He never knows what time it really is. So we want to focus on where the data errors are. W. Edwards Deming, famous quality control statistician, has a famous saying. He says, you cannot inspect quality in. Okay? You can inspect quality into a product. Well, a sample result from the laboratory is a type of product. And you can't inspect it in by going to the data validators and checking all the chain of custody and holding times and methods and blah, blah, blah. That's inspection. If it's the problem started in the field with the sampler, it's already happened. And what we'll see is there's something called the fundamental error, which is very insidious. It never goes away. And so you're stuck with it. And so that's why I call this whole thing error management. Okay? We never have certainty on what's going on out there, but we can manage errors to within tolerable constraints. And it all starts right here in the DQO process. Who's involved? Basically everybody. Now, having said that, I don't recommend you put everybody in the same room all at once for one meeting. You have too many people competing. Okay? You want to manage that, but the key things are, you know, senior program staff. You want your tech experts, stakeholders. They're probably ones you want to keep separate at first, except you and just maybe the PRP or the permittee. Senior folks, you probably want someone who's versed in sampling and statistics. You want QA/QC personnel. You might want to bring a risk person in because they may be one of the key end users, senior managers, and so on. It's up to you. The DQO process is flexible. You can bring whomever you want in at whatever point. And as I said, managing the politics and the size and so on, that's also an art, which we really won't get into today. Here's the DQO process in a very, very simple format. The first element is to state the problem. What is it you are trying to solve? What are you going to do with the data? Why are you out there? Okay? And it can be very simple, very short statement. We need to characterize. I mean, we just finished last year some high-level waste tank characterization program planning through the DQO process at Savannah River site. And this problem statement was fairly simple. We need to characterize the tanks so that we can get them closed under XXX authorities, and that was it. Okay? Got a little more complicated after that. What are the decisions that are going to be involved with closing those tanks or remediating a site or doing groundwater remediation? What inputs, what data do you need, what people do you need, what kind of budget might you need, all those sort of ancillary things that will come into play. What kind of time frame do you have? Actually, I've skipped to, number 3. What are the inputs to that decision? This is a time where you organize things. You look at global issues, as I said earlier. What are the big keys? What are we looking at? You know, how does the cost constraint affect the final product? How does our time constraint affect the final product? All those things. How do the politics? Whatever. You know, if you get into DOE sites, as I do frequently, you know, sometimes that's as big an issue as anything else. You know, how you work the way through the system and the various schedules and agendas that are out there. After you do kind of that administrative stuff, we get down more toward the what I would call hardcore planning for the sampling design. That is, what are the study boundaries? One of those is time. How much time do we have? Another one is physical space. Now, you may have a site, but that site may have several areas or sub-areas, and each one of those may have a schedule. What are the boundaries? Those boundaries are all dimensional, at least 2-dimensional, many times 3-dimensional, sometimes 4-dimensional, because time, especially in air and groundwater, time comes into effect. Are there cycles? Are there trends? In soils, we have cycles and trends, but they're flat, and they don't change over time. But in groundwater air, they do. And so we need to define very clearly so that expectations aren't violated, what are those boundaries? It gets a little complicated when you get into 3 and 4 dimensions, and we'll talk about that. These boundaries should also be fit kind of hand in glove with your conceptual site model. That is one of the global issues. What does this site look like? How is it operating? How is it contaminated? What's the history? What do we foresee in the future? Those type of things. What are the risks? What are the risk pathways associated with the site? Those things need to be set in the early phases. Oops, keep hitting the wrong one here. Early phases of the DQO process, because they will affect the boundary conditions that you put on later. The case I mentioned at Savannah River, waste tank, is very simple. Probably one of the simplest ever. It's the tank. Okay. Rule number 2. If you have any questions, see rule number 1. Okay. Now, it sounds silly, but that was as simple as it was. Later, that will grow, because then the boundary extends to, oh yeah, there's 51 of these things. Okay. And we have to think about them not just on an individual basis, but the whole constellation of waste tanks sitting there in Savannah River site, and how do they, once they're closed and 10,000 years and water starts moving through, how does that affect groundwater down gradient or in streams? And you do performance assessment modeling to figure that out. So many decisions at many different levels. The next step is to develop a decision rule. This is usually what they call an if, then, else. If this situation comes up, we do such and such. If not, we do the alternative. Or there may even be a series of alternatives. Usually people keep it to 1 or 2. At Savannah River, we were looking at things that were simple, like, if we get enough material for Savannah River not Nuclear Solutions, National Laboratory, to analyze, and we have met the cleaning conditions because they have to take as much of the sediment out as they can, then we can go on. It can be simple. If you have a threshold, say 400 parts per million of lead in soil, if the average in a industrial-sized area, maybe, 5, 10 acres, is below 400 parts per million, then no remediation or no further action is necessary. If it's above, well, then we have to have further action. So if this, then that. Very simple. The idea is to keep things simple, because what people saw in the past was we'd get to a decision point or a decision rule, and everyone would go, well, do we really have enough samples? All right, well, let's go out one more time, okay? And you get in this endless cycle. And so, the PRPs hated it, but in the end, so did EPA, because they were like, it never gets done, and they'd get heat for not closing any sites, and everybody remembers how long it took Superfund sites to work their way through the system. So the decision rule is really key. If you can get to that decision rule, and we'll talk about the other components of that rule in just a second here, then you can say, here's what we said we're going to do, here's the data we got, now we're done. Okay, it focuses everybody on a solution. Question, what does success look like? Okay, that's a key component in any project. When are you done? What does success look like? And how do we define that? That's what we do pretty much right here. Now, as part of that, we put limits on the error of our decision. And we'll go into that in gory detail, and that's where the statistics come in. Okay? You don't want to go out and take one sample. No one will believe you. Okay? I wouldn't. Okay? Well, would 2 be enough? Probably not. You need 1,000? That's too many. So, now we're negotiating. How many do we need? The big dog in the negotiating ring is the statistician, because he tells, okay, we got these samples and they're varying all over the place. We're going to need quite a few. Or he might tell you, you know what? It's pretty simple. We're getting a lot of repeated results. The conceptual model says that, it should be because it was this history, blah, blah, blah. and we can get off with just a very few. And we'll also see tomorrow afternoon some statistical tools that EPA and DOE have developed to tell us how many samples do we need according to the established limits of tolerable error. And finally, develop a sampling plan. They changed this from what was called optimize the design, which incorporated the economic elements. And I like that wording better, but we'll see in just a second that they changed their mind, and that's fine. It still works. This is probably only hard for me to see, but these are the same DQO steps, 1 through 7. Now, they've added sort of a branch here where decision making can be along a statistical line or it can be along an estimation line. And funny thing, even though I didn't really like the estimation kind of idea, it turned out to be very useful at Savannah River, because it turns out these high-level waste tanks weren't called high-level waste for nothing. These things are screaming. Okay, so you can't just send a person down and scoop a little bit of the material sludge that's in the bottom of the tanks. In fact, even when they bring up 30 to 70 gram a vial of material, they have to have leaded glass shielding and all sorts of safety precautions and transportation. I forget what they call it, devices, but they have a name for it. Anyway, it's not a trivial task. So we want to estimate, because this estimate is probably going to be made to be conservative at some high level of confidence, upped in other words, and then put in the performance assessment, which guess what? It's an estimate of things that are going to happen 10,000 years in the future. And I didn't bring my crystal ball because TSA doesn't like it anymore. And so if you have one, it helps, but it only works for about 100 years. And 10,000 years, sometimes I wonder if the performance assessments are real. And that's a good thing. You always need to question. So this is the new system. Again, at the bottom we have develop the sampling plan. I'll show you that I think it's very important to optimize according to economics and according to the statistical error that's allowed. What projects are covered by DQOs? Basically all projects should be. It can be a graded approach. You have a simple site, you can have simple DQOs. You have a very complicated site, you need more complicated DQOs. It took us 5 or 6 months at Savannah River, and we were working every day, meetings 2 to 3 times a week, just hashing through this, hashing through that. How are we doing the sampling? How do we get it to the lab? What's the lab going to do? How do we grind it? How do we do this and that? Okay, a lot of issues, because there was a lot of cost. These samples are about $1.5 million a piece. Okay, you think your sampling budget is bad? Try working at a nuclear site. The cost goes up very fast. So naturally, we wanted to minimize the number of samples. Okay, and we actually saved about $30 million by using an incremental sampling approach, and I'll talk about that tomorrow. So very important part. Again, results need to be applied toward a specific decision. Use these in the planning stage before the data are collected. It doesn't do you any good to plan after you get the data. I can't tell you how many times, and this is mostly now, thankfully, in the past, I did what I called retrofitting DQOs. People bring me data and they say, Jeff, what do we have? And I'll say, all right, I'll take a look at the data and I say, okay, based on what you did, here's what we can say according to the DQO framework. So, now I'm taking square pegs and trying to fit them back into the round DQO hole and say, here's how this plays out in the error management process and how confident you are in your decision. And naturally, there's some cases where things work out pretty well, and there are cases where there are some pretty major disappointments. And that usually meant more remobilization and additional costs. So you can use this, you always use it before, You can use it with either small or large studies, but again, it's a graded approach. You don't have to go into the detail and depth for simple studies, and again, the more complex the study, the more complex the DQO development. DQOs can be done iteratively, okay? Sometimes it's by accident. As I mentioned, people had to go back even though they didn't want to. Sometimes this is definitely by design. You want to go out, maybe simple, do a presence-absence study. Is it there? Maybe you can do that quick and cheap. Okay, field screening equipment, maybe, I don't know. But you don't want to send out everybody and their brother, lots of core samples, lots of lab costs, time, all that expense. If all you need to know, is it there? Okay, that'd be silly. Okay, if you find it, or if you don't find it, you go home. If you find it, cycle to the next one. Okay, now what do? Can we get it done in one fell swoop? Can we use the Triad approach, use field analytical? Or do we have to go in with the classic fixed lab approach? Maybe so. So maybe you do a field screening here, a Triad approach type, and then go back with a fixed lab for the final verification. I don't know. Lots of options, lots of ways to do this. But the idea is DQOs can change because you go through iterations. The site conceptual model may change as you go through the various iterations. As you learn more, you refine the conceptual site model and make changes. You probably, if you go through 2 or 3 times, and that could be in a triad also, even over a course of 2 or 3 days or a week or a month, as you keep finding the action line, the threshold values, and do, say, an adaptive sampling approach, you may go through this cycle very quickly, or you may do it annually. Okay, so the Triad approach. This has been very well applied over the last decade or two. It was something I got interested in and helped in over the years. We have systematic planning. DQOs fits right in this box. That's the upfront stuff. The Triad is a little bit more complicated than traditional because there are ways that you structure contracting. You may want to put more effort in the upfront portions, more money in the upfront portions. That's where the planning process comes in. Making sure that as a conceptual site model is either validated or refuted, people know how to make those decisions in the field with field analytical techniques so that you can keep accelerating the processes. And you don't have to come back and wait 6 months and analyze. No, we do it on the fly. So the systematic planning process is very important. As I just mentioned, the work plans are now dynamic. Okay? You are ready for change. That was a new concept 10 or 15 years ago. Before we had a SAP and a QAP safety plan. You went out and you did it. You got done, you came back and reviewed. And probably next year you went out and did it again. We don't have to do that anymore. With field analytical, we can have dynamic work strategies so that as the field analytical devices or techniques bring back sample data, we can say, oh, we're following path B, not A or C. And then we focus there. And everybody understands up front through that planning process what is going to happen because we found such and such a result. So it's a key part. And finally, as I just mentioned, again, real-time measurement technologies, field analytical test kits for PCBs or XRF or metals and soils, very good tools that can be used quickly and economically in the field to define the levels and extents of contamination. They have their issues, and we'll talk about those, but they also have distinct advantages from both the cost side on the polluter, so to speak, side, and the regulatory side as well. Again, here's some of the field screening techniques, X-ray, fluorescence, field kits for various things. There's a guidance out there. It's actually no longer TIO. I forget, it's TIO something or other. it's OSTRI, and I forget what that stands for. But same group, Dina Crumbling's been very active in that effort. Another key takeaway is that in my mind there are really two different types of DQOs, very, very separate and distinct in some aspects, but not totally. We have the laboratory side, and probably almost everyone is familiar with laboratory DQOs. Things like park parameters, the QA/QC options, what method are you going to use for the analysis, what's the analytical error associated with that analytical type, levels, and what kind of precision, accuracy, bias, and so on are introduced at the laboratory during the analytical process. Probably everybody here knows that very well. What is a little less known, and probably why I'm here today, is the statistical side of DQOs. As we mentioned, the key thing, number one, is sampling objective, sampling sufficiency, one of those questions I always get asked, how many samples do we need? How uncertain are we on either the mean or other parameter that we're trying to monitor? In the end, what's the uncertainty on our decision that we make, whether we use the mean or something else? What are the type 1 and type 2 errors? Where do we go wrong? Okay, how often do we go wrong? And if we were to go wrong, what are the consequences, both on the regulatory and let's say the PRP side? What are the implications, cost, and so on? Questions such as, do we use composite versus grab? Now, if you're in a environmental group, usually if you want to get some real emotion stirred up, start a conversation about the advantages of composites versus grab samples. Okay, usually get some people fired up. People have very strong opinions. We're going to address that a lot over the next 2 days. And finally, something called the fundamental error. This is something we never wanted to hear about, but fortunately we did, because there is a way to manage it. It's that insidious one I talked about that really drives sampling error. Okay, early phases. Check. We'll do for a break here. Okay, different questions may be asked in different stages of the project. Okay, do we have presence or absence of a given contaminant? Okay, what's the chance that there's a hot spot? Is there an old dump out there? Or is there a spill? Or is there a plume from something? Is there one there? And what are our chances of finding it on a certain level grid or certain size grid? Do the hourly readings of a given air contaminant violate limits versus the daily, monthly, annual limits? Okay, so we're bringing in different components. Those are the early phase. Again, it could be an average that we're worried about, or sometimes we want to know what is simply the statistical distribution of the soil samples, or are two distributions the same? I did a lot of work at Umatilla Chemical Depot over in Umatilla, Oregon, or Hermiston, Oregon. And one of the big questions was, they said, gee, Rocky Mountain Arsenal made all this stuff in like, Elizabeth, how many? 70 batches maybe, roughly? Something like, a lot of batches. And they'd send it to either Umatilla or Tooele, Utah. And the question is, we had a lot of data from Tooele. Could we use those data to help us guide our sampling at Umatilla? And they said, well, you have to prove the distributions are the same. And so we said, well, if the first, X number of ton containers went to Tooele, and then the rest went to Umatilla, we're out of luck. But what we found out was within a batch and within batches, they were like, it was almost like a shuffled deck of cards. Not perfectly, but enough so that we were able to use, to some extent, some of the information that had been paid for by Tooele and the Army to clean up the Army's other problem at Umatilla. So it's a simple question, but sometimes hard to demonstrate whether statistical distributions are the same. Later on, we see if areas around the smelter might be contaminated and how far out. I've done a lot of smelter work. It's very interesting. Or has the size of a plume increased or decreased? We may know it's there. It may have been there for years. What's it doing? Okay, is it shrinking, staying the same, getting bigger? So these are later questions. What is the question to be answered? Is a major DQO theme? What is the statistical population of interest? And what are the levels of error? Sounds a lot like my basic 3 questions. Okay? And so, in summary, we have a 7-step process on DQOs. We need to define the problem. We need to use resources efficiently. We have a strategic planning process that helps us. That's central to the whole thing. Managing our decision error is key. We need measurable criteria, that decision statement that I mentioned. And finally, we probably are going to have to tie into either a risk-based or some kind of threshold approach for decision making in the end. And I'm going to go through those real quickly here because we're out of time for this module. But this all integrates with geostatistical error management, the DQO process. Okay, again, GEM is about making decisions in the face of uncertainty. I started in the mining industry, and they had to mine ore with uncertainty. Is it really ore, or is it really waste? Okay, they have the same kind of problems we do. Is it high value? Is it low value? Okay, in terms of concentration. GEM uses 3 things: data quality objectives, sampling theory, and geostatistical appraisal. And when I say geostatistical, there are 2 types. One is the spatial, we'll talk about later this morning, and the other is sort of global geological, statistical, environmental / whatever type of statistics. Geostats was developed in South Africa by a guy named Georges Matron, and finalized by a fellow named Danny Kriega. And if you've ever heard the term kriging, and you will if not later this afternoon, it was named eponymously after Danny Kriega. Again, here are the most common questions. You know, how many, where, when, and what level of confidence, and can we keep the budget down? Here's where GEM fits in. We have the 3 GEM parameters or components up here. They fit in along with legal, regulatory, risk, laboratory, analytical, all the myriad other parts of a project that have to come together at once. But it's been amazing over my career how often something like the geostatistical appraisal, which is managing the error, has been the real driver for how things get done or if they get moved forward. I'll tell you a story about that later on. But it all affects the ultimately site characterization, how well do we think we know what's out there, and the decision making. Okay. We look at the integration of GEM with, say, a risk-based approach. We define an exposure unit. How big an area will people be exposed to, or eco receptors? How many samples and how much uncertainty? We see that the risk, I call it the risk cascade. We start with a statement of acceptable risk, like 10 to the -6th. We convert that to what kind of a dose would a person need to have in order to put them at risk at that level of 10 to the -6th. So that's the next step. Then we say, well, what kind of concentration from drinking groundwater or from the child in the sandbox eating the dirt? And they do. What concentration in the field would it take to get that dose, to get that risk, as we work back up the ladder? And then, how many field samples do we need to make sure we have a handle on a concentration which affects the dose, the risk? Sounds like, I don't know why I swallowed that fly, but we have to go through that process. And so people always want to know this box, and this box is driven by the GEM components. Okay, it's a TQM approach. Really all I want to say, quality by design. I mentioned W. Edwards Deming. You design the quality in, You don't inspect it in later on. And so we can keep up with our breaks. I'll end. Are there any quick questions before we take a break?